Welcome to MathGPT. Today, we're going to explore gauge theory, which is one of the most profound conceptual frameworks in modern physics. Gauge theory provides the mathematical foundation for understanding the fundamental forces of nature and underlies the Standard Model of particle physics, which is our most successful theory of elementary particles. Let's start with the question, what is a gauge theory? A gauge theory is a type of field theory whose Lagrangian, which describes the dynamics of a system, remains invariant under a continuous group of local transformations. By local, we mean that the transformations can vary from point to point in spacetime. The group of these transformations is called the gauge group. This local invariance, or gauge symmetry, forces us to introduce special fields called gauge fields, which manifest physically as force-carrying particles or gauge bosons. In more mathematical language, a gauge theory can be described as a principal bundle connection on spacetime with a structure group G. To visualize what a gauge transformation does, let's consider a simpler analogy. Imagine we have a sphere representing Earth. At each point on Earth, we can define a coordinate system, such as compass directions of north, east, south, and west. A gauge transformation is like rotating these local coordinate systems differently at each point. In physics, these coordinate systems represent internal degrees of freedom, such as the color charge in quantum chromodynamics or the isospin in the weak interaction. Now, let's examine the anatomy of a gauge theory Lagrangian. For a gauge group G with gauge field A mu, which takes values in the Lie algebra G of the gauge group, we can write down several important terms. First, we have the field strength tensor, also known as the curvature. It's defined as F mu nu equals partial mu of a nu minus partial nu of a mu plus the commutator of a mu and a nu. This expression generalizes the electromagnetic field tensor to non-abelian groups. Second, the pure gauge term, also called the Yang-Mills term, is given by the Lagrangian Lym equals negative 1/4 F mu nu with appropriate index contractions. Third, the matter coupling term describes how fermions interact with the gauge fields. This is given by the Lagrangian L, Dirac equals psi bar, times I gamma mu d mu minus m times psi. Here, d mu is the gauge covariant derivative, which equals the partial derivative plus Ig times a mu, where g is the coupling constant. The gauge invariance of the Lagrangian means it stays unchanged under the following transformations. The Fermion field psi transforms as psi of x to u of x times psi of x, where u of x is a local element of the gauge group. The gauge field, a mu transforms in a more complicated way. A mu goes to u times a mu times u inverse plus I over g times the partial derivative of u times u inverse. This transformation law ensures that the covariant derivative of psi transforms covariantly, meaning d mu psi transforms exactly like psi itself. Now, let's discuss the Standard Model gauge group. The Standard Model is based on the direct product of three Lie groups: SU3, color cross SU, 2, weak cross U, 1, Y, where Y stands for hypercharge. Let's examine each component. SU3, color is the gauge group of the strong interaction or quantum chromodynamics. It has 8 generators, corresponding to 8 gluons that mediate the strong force. Quarks transform in the fundamental representation, which is a triplet, meaning they have 3 color states, red, green, and blue. SU2, weak is the gauge group of the weak interaction before electroweak symmetry breaking. It has 3 generators, corresponding to 3 weak gauge bosons, W1, W2, and W3. Left-handed fermions transform as doublets, while right-handed fermions are singlets under this group. U1. Y is the gauge group of hypercharge, with 1 generator corresponding to 1 gauge boson B mu. Each field in the Standard Model carries a specific hypercharge value. Now, let's look at the direct product structure of the Standard Model gauge group. Since the 3 gauge groups SU3, SU2, and U1 are independent and commute with each other, we can write the full gauge covariant derivative as the sum of contributions from each group. The covariant derivative is given by d mu equals partial mu plus IGSG mu ATA3 plus IGW mu ITI2 plus IG prime YB mu. Here, GS, G, and G prime are the 3 gauge coupling constants. TA3 are the generators of SU3, TI2 are the generators of SU2, and Y is the generator of U1. This direct product structure is a key feature of the Standard Model and reflects the fact that the strong, weak, and electromagnetic forces can be treated independently each with its own coupling strength. A crucial aspect of the Standard Model is electroweak symmetry breaking. The Higgs boson, represented as a complex scalar doublet, acquires a vacuum expectation value, breaking the SU2 times U1 symmetry down to U1 electromagnetic. The Higgs doublet transforms as a singlet under SU3, a doublet under SU2, and has hypercharge 1/2, which we can write as 12 underscore plus 1/2. It acquires a vacuum expectation value of 0, V over square root of 2, where V is approximately 246 GeV. This symmetry breaking mixes the W3 and B bosons into the physical photon, A, and Z boson through a rotation by the Weinberg angle theta W. The rotation matrix that performs this mixing is shown here. As a result of this symmetry breaking, the W and Z bosons acquire masses given by MW equals GV over 2, and MZ equals square root of G squared plus G prime squared times V over 2, while the photon remains massless. Let's summarize what we've learned about the Standard Model gauge sector. The complete Lagrangian of the Standard Model consists of several pieces. First, the strong interaction term, which is -1/4 G mu nu G mu nu. Second, the weak interaction term, -1/4 W mu nu W mu nu. Third, the hypercharge term, -1/4 B mu nu B mu nu. Fourth, the fermion terms, which include all quarks and leptons in their respective representations of the Standard Model gauge group. And fifth, the Higgs terms, which include the kinetic term d mu phi squared and the Higgs potential V of phi. In conclusion, gauge theory provides a powerful mathematical framework for understanding the fundamental forces of nature. The Standard Model, based on the product group SU3 times SU2 times U1, successfully describes 3 of the 4 fundamental forces and has been extensively verified by experiments. However, it's worth noting that gravity is not included in this framework, and the quest for a unified theory of all forces remains an active area of research.